morning, everyone. Thank you all for being here, and also thank you for your attention for this talk. My name is Kievit. I'm the CEO at Qblox, and what I'll be talking today is actually about what we're doing at Qblox from a control perspective in bridging the gap between classical and quantum computers. And just to give you a bit of understanding of where you can position Qblox in the kind of the full stack of a quantum computer, is if you look at this image, you can actually see quite a few of the building blocks to make up a quantum computer. And there's a lot of complexity into aligning everything together. So what we did at Qblox is we said we want to do one thing and do that one thing really well. And that is control and measurement electronics, which you see here on the yellow brick. So just to give you a bit of understanding is what is a control stack for a quantum computer. So you see that here in this image. So we basically go from high-level user algorithms, and we have to translate that into electrical pulses interacting with qubits. And as you can imagine, qubits only live for a very, very short amount of time, and we also have a quite wide variety of qubits out there. So we have to have very high electronic precision and a lot of speed in doing this. So Qblox actually originated from QTech, which is quite well known in Delft, of course, which is coming from TNO and TU Delft, and we reside in a very vibrant ecosystem in Delft, basically ranging from startups, scale-ups, corporates, and also academia within the quantum realm. And they actually all contribute to different elements of those building blocks. And since we've grown, since we were founded, we've grown quite tremendously and achieving growth rates of about 400% every year. And we're currently at about 70 team members and still expanding that further. We are just about to move to a new building in about a month, and we're currently supporting about 80 labs in 4 continents. So what do we do in basically one sentence is we create scalable control stacks that enable useful quantum computing. And what that means is we actually have to look at what does a quantum computer need today, and also what do we need into the future. So we're also involved with quite a few developments towards useful quantum computing. Just to name 3 as an example, is we're working on quantum error correction with systems up to 1,000 qubits. We're working on quantum networks, where we have quantum computers basically talking to each other across the span of Europe. And also what I focus on a bit today is HPC integration. So not just a quantum computer, but actually have hybrid setups. So what do we see is the path to get to useful quantum computing? So if you look at 2023, we're somewhere in the range of tens or 100 qubits that are becoming practical and useful, but we're still not there at implementing useful algorithms just yet. There's going to be a few intermediate steps, and the one that we see as the most upcoming, and Professor Aspect also mentioned this, is the NISQ domain. That's where we're already quite close to actually get meaningful and useful results. We still have to kind of improve on the error rates. So we're roughly there with the number of qubits, we actually still have to improve on the error rates. But that's within, let's say, reach. Further down the line, we're of course going to look also at these perfect quantum computers. So think about fault-tolerant quantum computers. We're also working on those developments, but still there's quite a few years of further improvements to be done. So let's look a bit at where we are today and also the challenges in current qubit tuning and characterization. So basically scalable quantum computers, the running of NISQ algorithms and what are the bottlenecks, how can we improve that, and finally also this just briefly on fault-tolerant computing, but that will not be the focus of today's talk. So when you look at scalable quantum qubit tuning, and you see this in this image, we have to look at what is important to do this successfully. So what you see on the left side is basically an algorithm that has to go through a control stack, interact with the qubit or the QPU at the bottom, and then get to a result from that qubit. And there's very different, quite a wide variety of qubit technologies. So think about superconducting, spin, trapped ions, and many more, and they all have very different requirements. So what we do is we focus on having a good software interface, which we developed together with Orange Quantum Systems called Quantify, which is an open source platform to translate user algorithms into low-level assembly language, and then focus on the hardware. So in the hardware, we do 3 things very specifically. We focus on modular and integrated hardware, we focus on very fast hardware, and we focus on analog excellence. So the quality of the signals has to make sense. So let's look a bit at what does modular quantum control modules mean. So as I mentioned, there's still a wide variety of qubit platforms, and we have to make sure that for every different user, you can mix and match basically what you need. So I have different control modules that send signals, both in the lower frequency regime as well as in the high frequency regime. And then you of course have to read out the pulses as well, so we need readout modules. And a nice part about this approach is that this all fits into one cluster, and you can also grow with the development of the platform. So you can start with a 2-qubit setup, go to a 4-qubit setup, 20 qubits and so on, and still do that all from the same platform, and also switch between different qubit or QPUs. We also offer voltage and current sources to basically make it a total package for the research. So what does fully integrated mean? So if you actually look at, let's say, a 20 qubit setup, you need quite a lot of hardware to control that. And just as an example, to do a proper control and readout, you need readout analyzers, you need central controllers, AWGs, local oscillators, IQ mixers, and you can imagine this is becoming a large stack with a lot of different equipment that is not talking to each other. So that's what we focused on, basically condensing all of this into these clusters, where all of those, the equipment you see on the left, is condensed into one cluster mainframe of a 19-inch rack. The nice part is also these racks can be stacked on top of each other. So then you go into a tower, so if you go to a 100-qubit setup, that is all condensed within one platform. So how do we do that? We basically looked at all the hardware components that are necessary and bundled them onto these modules. So there's sequence processor to help you basically shape the pulses, local oscillators, DACs, IQ mixers, and we actually send out direct RF pulses straight from that hardware. Now, why is that relevant? Because we need all those signals, both from the low frequency regime and the high frequency regime, to be immediately generated and also talk to each other. So we now have a platform that is scalable, that is modular, but that only makes sense if they all can talk to each other. Because if we're talking about a 1 or a 2 qubit setup or a 20 qubit setup, as we move towards logical qubits, we also need to basically interact the output of one qubit with the output of another. So that's where we focused on sync and link protocols, which basically means that all the modules can start at the same time, so they're synchronized within much less than a nanosecond, and also the output comes within 350 nanoseconds to each other. So we can also use the output of one qubit to use as an input for the next one. So why is this relevant? Because it is about time. If you're talking about a 1 or a 2 qubit setup, this is an example of a tune-up of a 2 qubit transmon system. In the conventional way, this would take about 90 minutes. Now 90 minutes is still doable, but you can imagine if you go to a 20 qubit setup, doing that about tenfold is going to take a long time. So we've actually been able to reduce that from 90 minutes to 13 seconds. The last part is about lowering error rates. So we of course need to have high quality signals. So it's not just about scalability, syncing everything, but the quality of the signal needs to be good. So we're continuously focusing on having extremely accurate electrical signals with it, low spurs, a very, very best-in-class 1/f noise output, and have it extremely stable also at different temperatures. So the last part, just to go into the kind of running of NISQ algorithms, is let's look at what is the bottleneck there. So if you again look at this image, in running NISQ algorithms, we have to look at this 10 microsecond of communication. So what we did is we looked at what are the bottlenecks in actually doing that communication from a quantum perspective. So this is a Kawa algorithm, which is quite common in the NISQ domain. And we actually looked at how long does that currently take and what are the bottlenecks in doing that. So without going into too much detail, just to show the kind of the end result, if we run this algorithm, 98% of the time that it's taking is still being done in the classical computing approach. And only 2% is actually done on running the quantum algorithm. So there's a lot of improvement to be made there. And this is also where we see that quantum can actually use a lot of the help from HPC, because HPC is much better at doing this than what we are able at to doing this. So we have to look at optimizers and compilers and improve that and optimize that. So that's also kind of our message also here at Q2B, is we can do one thing and do that really well, but I think for the whole community as a whole, none of the companies can do all of it together. We focus on the hardware, but we have to look at the combination of QPU, GPU, and CPU, and really push the whole domain to the next level. So the fault-tolerant computing is something that in the 10 minutes that we have today, we cannot cover, but what I want to give as a last message is that we are here also to collaborate. We focus on one thing and do that really well. And we'd also like to invite you both at this event, but also at the drinks organized at Quantum Delta to basically collaborate and set up connections.